Right, yesterday you had a worksheet that dealt with different types of things with respect to functions. These are things that are a little bit different than what you're normally used to. Looking at local maximum minimums, looking at average rate change of a function, and looking at a difference quotient. All these are algebraic skills that can be related to things that you've done in the past in the algebra, but it's just going to be named a little bit differently. Solutions were provided for you. Questions you have about any of the problems? Anything you need me to go through? Yeah. Number 10, difference quotient. Once again, a difference quotient is something that when you get to upper level mathematics and you deal with calculus, this is an idea that you'll utilize in regards to calculating a derivative. But for right now, we're just going to call it difference quotient. We have a function f of x equals x squared plus 4x plus 1. We have to evaluate this function at two different things. We have to evaluate it at x plus h, and then we have to subtract off the evaluation at x, which is just our function. So when I evaluate it at x plus h, wherever I see an x, I'm going to put in an x plus h. So we have x plus h squared plus 4x plus h plus 1. Wherever I see an x here, I'm going to replace it with an x plus h. And then we're going to subtract off the entire f of x. So f of x is x squared plus 4x plus 1. And this is all over the value of h. Common mistake is not to quantify the f of x. Now it becomes an algebraic problem. As we talked about yesterday, x plus h quantity squared is x plus h times x plus h. So multiplying that out, is x squared plus 2xh plus h squared. Distributing your 4 through. We have 4x plus 4h. And then we subtract off, use our distributive property, take a negative sign to all three of the terms. All these second terms will cancel with something in the first term. The x squared will find something to cancel with here. The 4x will find something to cancel with here. And the negative 1 will find something to cancel with here. So we're left with 2xh plus h squared plus 4h. And this is all over h. Everything else cancels. And we look to cancel an h out of all three of the all the terms. So you're left with 2x plus h plus 4. Once again, this will be thrown into what is called a limit. When you get into calculus, there's a limit. And the limit will be, h will be approaching a value of 0, so the h's will cancel out then. So you're left with 2x plus 4. Any other questions? Once again, what you're developing there is a algebraic expression, a rational expression that you have to simplify down to the difference quotient. Anything else? Once again, there's a lot of different things in this chapter in regards to functions. Today we're going to talk about piecewise graphs. So once again, you've done graphing, you dealt with graphing, but you've never dealt with what is called a piecewise graph. When you're dealing with a piecewise graph, you're talking about a function that's defined as two different equations, two or more different equations, depending on the conditions for your x value, your domain values. For example, our function f of x is defined as two different types of functions. This function f of x or y is equal to x plus 1 when x is less than the value of 1. Okay, these are conditions over here. These are domain. These are domain conditions. When our x value is less than the value of 1, y is equal to x plus 1. When x is greater than or equal to 1, y is equal to 2x. And we want to be able to graph this. Let's first take a look at just function values. If I ask you, what is the function value at a value of 0? What is the function value at the value of 0? Well, what I'm asking you for is, first off, you take a look at the domain conditions. My x value is a value of 0. Is that less than the value of 1, or is that greater than or equal to the value of 1? Well, hopefully we can say 0 is less than 1. So if 0 is less than 1, then I'm going to go to this line here to be able to calculate what is my function value at 0. So I have 0 plus 1, or a value of 1. What is your function value 2? Then what is your function value 1? Kylie, what's our function value 2? 4. We have to use the bottom one because we're greater than or equal to the value 1. 2 is greater than or equal to the value 1. So I have 2 times 2, which is 4. Then if I equal 1, Courtney, what's our y value? 2. Because I'm equal to a value 1, I'm going to use 2 times 1, which is a value of 2. So if we take a look at the graph of our function, I used to teach us by, like getting the x values, plug in the x values, solve for y values, and plug in, and then graph the ordered pairs. But I found it's a little bit easier to take a look at it in a different way. You are graphing two different lines or two different functions. You're graphing y equals x plus 1. We want to graph y equals x plus 1. Well, if I'm graphing y equals x plus 1, I'm hoping to say that my slope is a value of 1 and my y-intercept is a value of 1. Okay, just looking at slope and intercept. So if I'm graphing this line, y equals x plus 1, I can put a dot at 1 because that's my y-intercept. Then I can go up 1 and to the right 1 and put another dot. And this is y equals x plus 1. Now we take a look at the domain conditions, and what you'll have to use is you have to use an eraser with this now. But I found this is easier to look at it this way. If I was just looking at x is less than 1, and I was going to graph x is less than 1, what would the graph of that look like? Okay, so what would the graph of that look like? X is less than 1.
It'd be a straight line or horizontal line.
Yeah. X is less than 1. What do I put at 1? Okay, you'd have an open dot at a value of 1. And then what? What would be values that are x that are less than the value of 1? Which direction would we go? Left. So this is x is less than 1. So what I want to do with my graph here is I want to signify and only utilize values of x that are less than 1, which I want to utilize the same idea. I'm going to have an open dot at this value of 1. And I want my graph to only go to the left. And this is where your eraser comes in. So what we have is we have an open dot ray. If we have y is equal to 2x, we have a y-intercept of 0 and a slope of 2. So we start at 0, we go up and to the right 2. So here's your y equals 2x. But this is only true for values of x that are greater than or equal to the value of 1. So at my x value of 1, what would we have? Would we have an open dot or a solid dot? Right? A solid dot. So we would have a solid dot here, and we would go to the right. So we want to signify that in 2 dimensions now. So I'm going to get a solid dot here at the value of 1. So basically, we have an open dot we just filled in. Sometimes that will happen, sometimes that will not happen. If we look at the second one, we have 3 graphs. Y equals x minus 1, y equals x, and y equals x plus 1. We first look at the first graph. And hopefully we can say that the slope is a value of 1 and the y-intercept is a value of negative 1. So on our graph, we're going to graph y equals x minus 1. And our y-intercept of negative 1, go up to the up 1 and to the right 1. But now we have the condition of the domain that we have to worry about. These are only for the x values that are less than the value of negative 1. So if I'm graphing x is less than negative 1, Cole, what would that look like? X is less than negative 1.
That would be an open dot going to the left.
Opened out a negative 1 going to the left. So in my graph up here, that's what we want. We want an open dot at the value of negative 1. And we want to go to the left so we can use our eraser and take us back to that. Once again, once you've done a few of these, you'll start anticipating and not having to go too far in regards to your graphs and erasing as much. Y equals x, slope of 1, y-intercept is 0. So we go up 1 to the right 1. Now, if we look at the interval, -1 is less than or equal to x, which is less than 2. Q, what would this graph look like? If I have -1, if I'm greater than or equal to -1, and less than the value 2, what would that look like?
A closed circle at -1 and an open circle at 2.
So there's my graph, an open dot at -2, solid dot at -1. So I want my graph that I just graphed to look the same. So we're going to get a solid dot at -1 and an open dot at 2. And y equals x plus 1. We have a slope of 1, y-intercept of 1. Go ahead and finish your graph out. And we have to be greater than or equal to the value of 2. Should give us a solid dot at the end of the array as an endpoint. Going upwards to the right with a slope of 1. Some of the graphs, once again, will connect like we did the first one. Some of them won't connect. But if I take a look at this graph, is this still a function? Does it pass the vertical line test? Yes, it does. Well, you sit there and go, okay, well, the vertical line test, what if I draw it through there? Well, I intersect this graph at this solid dot. This is an open dot, so it's not actually a dot. Okay, so it still passes the vertical line test. Two other types of functions. The greatest integer function. Is a bracket without the top there. The greatest integer function. This means the greatest integer, not greater than x. In my mind, I have to run this through my mind and say these things each and every time. What is the greatest integer not greater than 1? The greatest integer, integers are positive, negative, whole numbers. What is the greatest integer not greater than 1? Jack, what do you think? 1. Is 1 greater than 1? No, it's equal to. What is the greatest integer not greater than 1.2? 1. What is the greatest integer not greater than 1.7? Data? 1. 1.9, still valued 1. But when I say 2, what's the greatest integer not greater than 2? How many what would we have? 2. And then all these would be 2. And then we jump to 3. Well, if we take a look at our graph, I start plotting points. If x equals 1, y equals 1. X equals 1.2, y equals 1. 1.7 and y equals 1. 1.9, y equals 1. What if I want 1.9? Okay, so what would we still be at? 1. But when I hit 2, I have to hop up. What do you think happens at the end point here? An open dot. And I have a line. Then I do the same thing with the 2's. When I'm at 2, I hop up to 2. 2.2, I'm at 2. 2.7, I'm at 2. 2.9, I'm at 2. 2.99, I have 2. And then we get our open dot. And we follow this pattern throughout. If I want to go between 0 and 1, I'd have a solid dot here, an open dot here. -1, solid dot, open dot. What type of function do you think we call this? What are we forming there? What do they look like? Anybody? Steps. Yeah. What's the step function? This is a step function. The least integer. Don't know if my voice is going to make it. You had COVID 3 weeks ago, then I don't have to worry about this stuff. You guys don't have to worry. The least integer function is the smallest integer not smaller than x. The smallest integer not smaller than x. once again, I have to say anything for you. I ask. Anything to make your life easier. I'm here for you. Once again, I have to say this in my brain all the time. What is the smallest integer? Not smaller than 1. The smallest integer, not smaller than 1. Oh, and what do you think? What is the smallest integer? Not smaller than 1. Because 1's not smaller than 1. What's the smallest integer? Not smaller than 1.2. 2. 1.7, 2, 1.92, and then 2 would be 2. Then if I go 2.2, 2.7, 2.9, all these are going to be what, Todd? 3. So looking at our graph, at 1.2, we're at 2. 1.7, we are at 2. 1.9, we are at 2. 2, we are at 2. Where does our open dot now go? What if I have 1.00000000001? I'm still at 2. So what happens is the open dot switches to the other side. But we still run the idea of a step function. At 1, we're at 1. So I have open dot on the left, solid dot on the right. And once again, we get a step function. What we have here is some graphs, some piecewise graphs. They have some greatest integer least integer functions on the back. Solutions, I posted them also. The rest of the time is yours.